Okay, so to recap what I've been doing on my blog, I'm interested in a family of graphs known as the distance transitive graphs because they are highly symmetrical, and so there is a certain rarity or exceptionality about them. In fact, it seems promising to work on the general problem of classifying the distance transitive graphs because we now know that there are only finitely many distinct distance transitive graphs of any given valency greater than 2 or any given eigenvalue multiplicity greater than 1. Bearing in mind that I'm talking about connected simple graphs here when I'm talking about graphs. More generally, this is true for distance regular graphs, whose adjacency algebras are a special kind of coherent algebra with lots of additional structure. And so I would like to go over how ideas about duality in coherent algebras have been useful so far towards tackling various instances of this problem of classifying the distance regular graphs, and perhaps more interestingly, the distance transitive graphs. So, by a coherent algebra, what I mean is a space of complex square matrices that's closed under transposition, as well as matrix multiplication and Shor product with identities, where by Shor product I mean the entry-wise product for matrices. And in addition to the adjacency algebras of distance regular graphs, there are a number of prototypical examples of coherent algebras arising from finite groups. For starters, recall that we have group coherent algebras of finite groups, coherent algebras that can be identified with group algebras of finite groups in the usual sense of the term, under convolution. Then from there, recall that we always get a commutative coherent subalgebra of the group coherent algebra of a finite group through summations of matrices representing elements of the group lying in the same conjugacy class. And in addition to conjugacy class coherent algebras of finite groups, recall too that we get coherent algebras as commutants of representations of finite groups as groups of permutation matrices. So, to tie together the prototypical examples of coherent algebras that I've drawn from my blog so far, it might be worth noting that if we're, say, working with a distance transitive graph or distance regular graph, we get a number of additional coherent algebras arising from its automorphism group as well, with at least the latter kind containing its adjacency algebra as a coherent subalgebra. Okay, so to start talking about duality in coherent algebras now, I think it is important to first recall the central fact that commutative coherent algebras have pairs of dual bases consisting of both their primitive matrices relative to Shor product and dually their primitive matrices relative to ordinary matrix multiplication as well, which I too have addressed in detail on my blog. By a primitive element in a coherent algebra, what I mean is an idempotent element M, such that the product of M and any element in the coherent algebra lies in the span of M. And from here on, by a primitive element or a primitive matrix in a coherent algebra, I will always mean a primitive matrix relative to ordinary matrix multiplication for brevity. And I will distinguish elements of a coherent algebra that are primitive relative to Shor product as Shor primitive matrices. What makes these dual bases of commutative coherent algebras quite central to talking more broadly about duality in coherent algebras are the related constructions of character tables and dual character tables of commutative coherent algebras. We construct a character table for a commutative coherent algebra from the coefficients we get when expressing its Shor primitive matrices as linear combinations of its primitive matrices. We also get a closely related dual notion of a dual character table of a character table of a commutative coherent algebra, where the dual character table of a character table of a commutative coherent algebra is actually just its inverse, scaled by the order of the matrices in the coherent algebra. Perhaps even more interesting is the fact that the entries of the dual character table of a character table of a symmetric coherent algebra are specific rational multiples of the corresponding entries of the transpose of the character table. Now that I've gone over some of the character theory of commutative coherent algebras, I think it makes sense to talk about what it means for a pair of coherent algebras to be dual to each other. So a pair of coherent algebras are dual to each other if there is a duality mapping between them. And a duality mapping between a pair of coherent algebras is a linear isomorphism that makes the matrix multiplication structure of the former compatible with the Shor product structure of the latter, and vice versa, in the sense that I've displayed here. This definition of dual coherent algebras makes sense because, for one thing, a pair of dual coherent algebras is equivalently a pair of commutative coherent algebras for which character tables for one are dual character tables for the other, and vice versa. Although this can be stated in terms of conjugates of character tables, since conjugates of primitive matrices are primitive in a coherent algebra, which will be useful towards talking about stronger variants of what it means for a coherent algebra to be dual to itself. But even better is the fact that a pair of dual coherent algebras is also equivalently a pair of commutative coherent algebras for which the intersection numbers of one are the dual intersection numbers for the other, and vice versa. The intersection numbers of a coherent algebra come from expressing products of pairs of its Shor primitive matrices as linear combinations of its Shor primitive matrices. There is an analogous dual concept of the dual intersection numbers of a commutative coherent algebra. There are also dual concepts of metric and cometric coherent algebras, with metric symmetric coherent algebras actually being the same thing as the adjacency algebras of the distance regular graphs. And it is interesting that a coherent algebra is metric in a pair of dual coherent algebras, if and only if the other is cometric. since this gives additional constraints that the adjacency algebra of a distance regular graph must satisfy if there is a duality mapping on it, which could be useful towards classifying certain families of distance regular graphs. So now I'm going to start talking about self-dual coherent algebras, which I mean to be a distinct and stronger notion than that of coherent algebras that are just dual to themselves. And a prototypical example of a self-dual coherent algebra is the group coherent algebra of a finite abelian group, with a character table for the coherent algebra being a character table for the group in the usual sense of the term. And what's interesting is that a strong duality mapping on the group coherent algebra of a finite abelian group can be identified with a Fourier transform on the space of complex valued functions of the group in the usual sense of the term. And so the theory of self-dual coherent algebras kind of generalizes the Fourier theory of finite abelian groups in this way. Okay, so the connected strongly regular graphs are the distance regular graphs of diameter 2. And, like on my blog, it is possible to get general expressions for the character table and dual character table of a strongly regular graph from what I've gone over so far about duality in coherent algebras. And from this, it is possible to get a nice characterization of the self-dual strongly regular graphs in terms of their eigenvalues. By which I mean the strongly regular graphs whose adjacency algebras are self-dual coherent algebras. And from this, I further got a classification of the self-dual strongly regular graphs into two types of self-dual strongly regular graphs. And I'm not sure how to further classify the latter type of self-dual strongly regular graphs into families of self-dual strongly regular graphs arising from combinatorial designs yet, but I do know that the Latin square graphs are an example of a family of self-dual strongly regular graphs of this latter kind. But this classification of the self-dual strongly regular graphs did finally give me a nice characterization of the self-dual strongly regular graphs as the strongly regular graphs whose eigenvalue multiplicities are the valencies of their distance graphs. And I don't quite know what the distance transitive self-dual strongly regular graphs exactly are yet either. But I do know that the Hamming graphs are a prototypical example of a family of self-dual distance transitive graphs, which includes some self-dual distance transitive strongly regular graphs. Though I do think there are prospects to continue working on classifying families of self-dual distance regular graphs and their distance transitive subfamilies, building on what I've gone over here about duality in coherent algebras. And perhaps it would be interesting to, say, explore what the cometric strongly regular graphs are next as well.